Hello, everybody. This week, I was stayed in. I will go to Japan to join in the international conference, ISTTM at Yokohama. So I cannot attend our classroom. So I used iPad to record my lecture, and then I will continue the teaching material from last week. So last week we discussed about the paper from Samsung, and then they do a pretty interesting comparison between their nanosheet fat with film fat, and then this is the from figure 6. Figure 6 shows a typical the N fat and P fat ID saturation in the IOF. So usually this is a log figure. So this is because we like to the jolt log ID versus VG. So for leakage current, we must to understand to check is leakage current in log scale. So usually we use log scale to check the leakage, and for saturation. So it's very difficult to boost its drain current, and then the drain current is proportional to mobility, shear side, width over length. So it's impossible to boost the drain current in log scale. So usually we use a semi-log to we use semi-log to describe the performance of our transistor. So you can see that they set only 31% and 26% saturation current improvement related to film fat. Okay, so I think the reason maybe from width or maybe from mobility, but to my point of view, the channel material is silicon, and then for a MOSFET, they set 31% increased for a MOSFET. So this is maybe due to the width and the service, the orientation. So later, I think orientation effect here. Let me check. Okay, let me check. Okay, here. Later, I will talk about mobility from a different surface. So, like a film fat, I think like a planar fat. Usually, we fabricate the planar fat MOSFET on 100 surface, and then due to the 3D structure for film fat, and the top, the fin is only 5 nanometer only. It's only 5 nanometer. So the percentage, the area percentage of film fat from 100 is very small. So the main surface for conduction is 110. So as we read the mobility channel from Samsung, they told us 110 electron is 230, but for hole is 180. For 100 service, we got a higher electron mobility, and then the hole mobility is very small. So for FinFET, the service orientation could benefit PMOS, and for planar surface, for planar MOSFET, the 100 service could benefit the planar MOSFET or a gate-all-around structure, nanosheet structure. So later I will discuss it in detail. Maybe by the end of this month, I will discuss about. I will review this paper. Okay, so the reason for smaller DC improvement of PMOS compared to NMOS come from the mobility differences due to the change in channel orientation from 110 to 100. So as the device structure change from FinFET to nanosheet, okay, we can have a bigger width, and also we can benefit the mobility enhancement due to the conduction service is from 110 to 100. Okay, so next slide, I want to talk about the second generation of multi-bridge channel FET design and the performance. Last week I said I talked about the continuous here. The various nanosheet widths could be fabricated on the same wafer, use a direct pattern. Okay, and then we still have problem for substrate. This is because we use selective AP regorge for a second germanium. So we have to font a substrate area in different space at the same time. So here from the words, this sentence said that for the second generation of MEC FET for SF6 platform has more improved process on this item based on the experience from first generation. So for their second generation, they can achieve uniform epitaxy substrate growth in a nanosheet. The process for various nanosheet widths for nanosheet widths, and they said it's very challenging because of the substrate the volume gap for filling and the growth rate dependence on nanosheet FET. So due to this reason, the channel resistance of PMOS using silicon embedded substrate as the stressor increases at the narrow nanosheet devices without careful optimization. It means this problem is still, I think this module is still challenging. So although they can I think finish the epithelial growth for different space, for different widths, but they don't optimize the suction. And then I know it's possible and it's good to form silicon germanium, embedded silicon germanium. However, to provide a very high stressor to boost the hole mobility is very difficult. This is because for nanosheet they use inner spacer. This is nanosheet. They use inner spacer, and this is silicon, and this is the front. So the front is very small, and then the sidewall is static by silicon and silicon germanium, and then this is inner spacer. So this is outside. So the crystal sheet, the area of the crystal sheet is very small. So to provide to form a very good substrate impacted silicon germanium stressor is not difficult. It is not easy. Okay, and then as compared to for their novel second generation nanosheet has improved the substrate growth uniformity, but no stressor, and then the channel resistance gap reduction between nanosheet and the west nanosheet from 18% to 4%. So you can see that the channel resistance, since we want to fabricate different widths, N-FET and P-FET, and then the resistance, the difference of the resistance among these widths are very small. So it means they can provide a very uniform embedded substrate, and also the advanced silicon substrate process in their new platform has suppressed parasitic leakage current beneath rear nanosheet successfully, and realize ideal substrate slope value with uniform short channel immunity. So you can see that the substrate slope is very small. It's very close to 65 milliport per decade, and then I told you the minima substrate slope at the room temperature is about 60 milliport per decade. Okay, and then for the other issues they have improved is the nanosheet channel, because we have to use a plasma etching to release the silicon germanium, and also we have to deposit the different metal gate for multi wall function. This is because we want to include high performance, low power, and general property applications on the same wafer. So you can see that the first one, the damage on top nanosheet during metal gate process, and then the second one, a typical metal gate removal for multi-wall function, and then the third one, the wall function difference between inner and the outer gate. So that for PMOS and for NMOS, if you have different application, and then you have to adjust the VTH value. So but you know for during the process plasma etching process, during the plasma etching removal process, you have to face several challenges. You know, again, let me repeat it. The first one is damage on top nanosheet during metal gate process. The second one is the metal gate removal for multi-wall function. The third one is the wall function differences. So for metal gate process, different environment among each nanosheet. Gate dielectric damage during a material deposit and a strip process through a nano metal gate area, and the wall function uniformity between inner and outer gate should be considered. So to me, you must try your best to recover all the defect during the release process. Also, we have MOS and PMOS, and they have to use different metal materials to for different VTH application. So this is such issues have to be considered. Okay, so the VT gap among the several nano sheet width also improved from 50 millivolt to less than 20 millivolt with metal gate material tuning. Okay, so you may consider dipole. This is because the gap, the space between two fins is very small. So we don't have enough volume to fill in to deposit. I think we don't have enough space for different metal wall function metals. So dipole we call volumeless VTH adjustment, to use dipole to adjust its VTH. So we can have balanced VTH between N-FET and the P-FET. So let's say that from their perform, they don't suffer a VTH shift, even the channel, the fin width decreased from NS4 to NS1. So it means they don't worry about they have solved the issues, the wall function difference between inner and outer gate, and also they try to solve a lot of process issue. Okay, and then this is the gate leakage reduction with the metal gate process attenuation. So this is gate oxide damage improve. So the after etching process, so the channel would be damaged during the plasma because of the plasma. So this will be a big problem. So from my point of view, you can use RTO or I think rapid thermal oxidation or RTA to recover the defect caused by plasma treatment. So their nanosheet in this platform has achieved 30 to 40% of the gate leakage from their FinFET platform. So you may see that the gate-around structure is very useful to suppress leakage. So this is the fin structure, and this is the gate and the high K, and then nanosheet is a gate-around structure. Okay, so actually you can use gate-around structure to suppress the gate leakage, and then I think I think as compared to nanosheet structure, FinFET, the gauge of FinFET is large, is pretty large. Okay, and then I think that the next one is about contact. So for this paper, Samsung wanted to discuss about a nanosheet. Samsung wanted to discuss about the process optimization. So about the process optimization, you may discuss about Kerosite EOT, but however you don't need it to the EOT is very close to 1 nanometer, so it's very difficult to scale down the EOT, and then because of the fin structure, because of the nanosheet structure, so I think the EOT scaling cannot give you more benefit to boost your performance. Okay, and then I think the content is also important. The substrate is very important, but the content is also important. So additionally, the normal contact process with contact profile and feeding the material application has brought about 5 total overlap capacitance reduction from the MOE middle line, and 23% the contact resistance in similar contact dimension. So if you can reduce the overlap capacitance, and also if you can suppress the contact resistance, and your performance can be boosted. Okay, and then next one, I wanted to discuss about the variation in nanosheet. So PPA is about PPA. What is PPA? PPA is a performance, power, and area. And actually, we like to talk about. We like to discuss about PPAC. PPAC is power, performance, area, and the cost. So from this paper, let's set besides PPA improvement, because they give a detailed comparison from the VTH, from the substrate slope, from the I on and I off, and C overlap. Okay, so from these parameters, a nanosheet structure can outperform the FinFET a lot. So we can say that nanosheet structure can help to reduce the power and increase the performance. But about A is very close. So I think that we cannot satisfy all parameter, but we can boost performance with a lower power on the same the footprint area. Okay, so one of the nanosheet FET advantage is the variability reduction from FinFET, because nanosheet thickness, thickness and the nanosheet distance is defined by epitaxial growth. So it can provide a very good controllability and uniformity, not by photo and etch process. So if we use solver, so you can see that. So the black night is from a nanosheet, and then the distribution is steeper than that of FinFET. So I mean this is pretty good, and then you can use this structure to improve the to get a tighter distribution. So in this figure, a nanosheet has a 33 and 16 smaller variation at the N-FAT and P-FAT respectively, which will bring a clear benefit to chip level and leakage reduction. So about this paper, Samsung provide a comparison between two second generation of nanosheet, and then they talk about advanced structure, metal gate, middle line process for layer SF3 technology, and for F3 technology, the world first gate-all-around foundry platform with a huge performance, power, area gain over their FinFET platform. It's a that from this paper, actually they don't release they don't release enough information about their platform. I think it's quite common for manufacturers, I think a fab manufacturer to release any information. This is because they wanted to keep their secrets for to be more competitive, and then about the platform paper, they just give us how much percentage they have improved from I think from old platform to new platform. So they just tell you, they try to provide advanced structure, the metal gate, and then some process flow to improve their their devices. Okay, so this is the I think the platform paper from Samsung, and then the next year, after 6 months, they publish another paper in VSI. I say that VSI and the IDM are both important conferences for solid state electronics. So if you like, I encourage you to join this game because IDM and VSI are two very big conference, and then a lot of cutting edge technology will be released and will be discussed at the time. So from my point of view, you should join the IDM or VSI from day one to last date, and stay in a hotel just to attend the different sections, and then try to raise your hands to to discuss, to ask the speakers, and then you have to join the panel discussion at the night time. Enjoy the red wine, the white wine, and the juice, or the sparkling water. The I think they're pretty good, and some speakers was stand on the stage, and then they give you a very brief talk by 5 minutes, but you will spend 2 hours at the press to listen to a lot of challenges from the audience. So it is a very interesting I think experience to join the VSI and IDM. And then if you want to publish your paper, if you want to publish your paper at IDM or VSI, you must prepare a lot of figures for your paper, for VSI, I think the 12 figures for IDM, 24 figures are needed. Okay, so let's move back to this paper. So Samsung, the title of this paper is a product performance a third generation GA platform transistor designed with extremely small local layout effect and transistor variation. So so it's very interesting. So I think we have to focus on a product performance. So they discuss about different modules, okay, to boost their product performance. The first, I think this next one is the introduction. The gate-all-around FET is the next game changer with the dimension change and a gear. A gear is pretty important for bicycle or the autobike. Was already shifted from research to manufacturing stage as a platform technology in 3nm technology node, uniform gain and NP balance across various size layout of transistor variation to control a chip leakage and scale a dynamic power with a low VDD. In this paper, Samsung said that to overcome the constraint situation, the product well designed. So it's a product well designed third generation MBC FET with normal process is reviewed. Result in an extremely tight product control to maximum nanosheet benefit. So I think in this page I have discussed about that, the mobility. So the red is bad and the green is good. So the best one, I think the best service for electron is 100, and I think the best the service for hole is 110. So people say that this year's IDM 2025 I make use bonding process, CFET process. CFET will be discussed. Okay, CFET will be discussed. Later, in next semester about CFET, and then they use bonding process to integrate 100 and 110 process. Okay, and then another obstacle to maxima get around the DTCO is the NP ratio balance with high drivability due to the orientation difference and AP growth difficulties. So we must consider about that. So for FinFET, we can enjoy higher, the PMOS FET. So the drive current between NFET and PFET is very close. But now, if we change the structure from FinFET structure to nanosheet structure, we have to suffer different the problem, especially for PMOS FET. And then the second one is the substrate design. This is the normalized volume per each fin or nanosheet. So you don't need to worry about FinFET because they have isolate, a fin. So we just, I think that we just growed the suction area epithelially for fin fat. But for a nanosheet structure, we will have the different width. So if the transistor width decreased, and then the suction value will decrease a lot. So they are different. But for I think a fin fat, no difference. So it's impossible, to decrease the fin transistor width, because the width is very small. It's about 5 nanometer only. So if you want to change the drain current, you have to use different line. Use different lines. So for one, low leakage. If you need a higher performance, you can have 2 or 3, maybe 4 fins. Okay, but for nanosheet, because we will have the same the stack layers and the wider narrower or wider scale layers. Okay, for a narrower and a wider stack layers. So the suction area are pretty different between the narrower suction and the wider suction. Okay, and then I think the NP ratio for NFAT, the DC performance for NFAT is about I think the 0.8, but for a nanosheet we can have a very good balanced performance between NFAT and the PFAT. So normal suction process can provide a balanced NP ratio and a performance enhancement. Okay, so here you can see that the boundary is also a problem. The boundary is also a problem because the metal, if the metal gate for PMOS is very close to I think close to the fin for MOSFET, and then the metal the metal were induced, or to influence the VTH adjustment. But you can see that the surface area is very small for the side wall. So I think the metal gate boundary effect is not important. Okay, and then let's talk about FinFET and the CFET. So this is the FinFET. Okay, so this is the very weak point for FinFET because we may suffer a suction punch through. Okay, so it's very difficult to scale down. Okay, what is punch through? Punch through. This is punch through. So the suction punch through means if we add a higher drain current and the depression area will touch the drain side, the source side, and then the leakage can be sweep into source side. So we call this effect punch through. So punch through means I think the suction effect. So you will get I think the very severe dipole. So from this schematic diagram, schematics, so the dipole here are good, but here because we will suffer punch through effect, so the dipole increased. But for a nanosheet, the depot, the depot is very close, no change. So the variation about depot between FinFET and the nanosheet, nanosheet can provide a pretty good get controllability. Okay, and then the thickness is decided by AP, and the FinFET is decided by Hn. So channel thickness variation, the reduction, the nanosheet can provide a very good nanosheet, very good nanosheet, the variation. Okay, and then VTH, I think the same, because compared to FinFET, the VTH variation in nanosheet, global, total, and local are significantly reduced. So global, total, and local. So this is because the short-term effect can be suppressed. Okay, so this is the variation, the comparison between the FinFET and the nanosheet. So this is the normalized chip leakage. So the FinFET, I think the normal chip leakage for a nanosheet is a pretty good. Conclusion. Samsung published a new paper in VSI the last year. So they said it's the third generation designed for product performance. Okay, and then nanosheet game has been proven by the product as a promising technology for high performance, low power application to overcome both scaling and the energy issue. Okay, that's for today's course. Thank you.